Hello, this is the third lecture on elementary geometry. This time, we're going to present to you 7 Japanese tempo geometry problems. These 7 problems are actually related. The first set involves 2 tangent circles and a common tangent line. From these 3 elements, we are able to construct a sequence of smaller and smaller circles. Each circle is tangent to the common line and one of the 2 given circles and the previous circles. The second set involves a given circle and a core, and a circle tangent to the core and to the north pole of the given circle. Then from this circle, we're able to construct some other circles. So the common issue is, what are the radius of these circles and what are the radius of circles? Surprisingly enough, these 2 seemingly irrelevant set of problems actually have a common base. So we're going to explain this in this lecture. So as we mentioned earlier, we will be presenting to you 7 related Japanese tempo geometry problems. These problems are divided into 3 sections. Section 1 covers a lemma and a problem 1 and a problem 2, which is actually the first set. Section 2 covers problem 3 and problem 4. Finally, section 3, which is the longest one, discussed problem 5, problem 6, and problem 7. These 3 problems simply combine the problems in section 1 and problems in section 2 together. Except for problems 5, 6, and 7. All other problems are very easy. However, problem 5 to problem 7 requires the use of parabola. And if you are not used to or not familiar with parabola, you may want to review the concept of a parabola in your geometry book. So the dependence among these problems goes as follows. We start with the lemma. And the lemma directly implies problem 1 and problem 2, which are in section 1. This lemma is also used in problem 3 and problem 4 in section 2. And finally, the results here and the results here are combined into section 3, in which we have problem 5, problem 6 from here, and combining problem 5 and problem 6, we have problem 7. Actually, problem 7 is a converse of problem 5. So let's start with section 1, which includes a lemma and 2 problems. Let's start with a lemma. This lemma may appear in your geometry book or as an exercise in your geometry book. So suppose we have 2 circles. The first circle has the center O1 and radius R1. The second circle has center O2 and the radius O2. Both circles are tangent to a common line, A and B. The distance between A and B is D. So our question is, what is the condition for these circles to be tangent to each other? This lemma states that these two circles are tangent to each other if and only if the length of the segment AB, which is D, is equal to twice of the square root of the product of R1 and R2. So let's prove it. We construct a perpendicular line from O2 to the line of O1 and A with perpendicular foot C. So we have a right triangle here. Now, if O1 and the circle O2 are tangent to each other, the distance of O1 and O2 is the sum of R1 and R2. Because this is a right triangle, so the square of this and the square of this should be equal to the square of the sum of the radius. As a result, we have D squared is equal to the square of this minus the square of this. Then we apply a very commonly seen formula, A squared minus B squared, being A minus B times A plus B. In this term, R1 cancels each other. So we have 2R2. In this term, the R2 and R2 cancel each other. We have 2 times R1. Therefore, D squared is equal to 4 times R1 times R2. Of course, D is equal to 2 times the square root of R1 times R2. So let's establish the converse. Let's assume that the distance D is equal to twice of the square root of the product of R1 and R2. Again, this is a right triangle. So the square of O1 and O2 is equal to the square of this segment and the square of this segment, which is here. Then O1C is R1 minus R2. D, by assumption, is this. Then expanding this and then simplify, eventually we reach the distance between O1 and O2 is equal to R1 plus R2. Of course, this implies that these two circles are tangent to each other. Therefore, the lemma is true. We're going to use this lemma throughout this lecture. So let's talk about problem 1. Problem 1 goes as follows. Given a circle of radius R1, another circle of radius R2. These circles are tangent to each other. They also tangent to a common line. So we have two circles tangent to each other, both tangent to a common line. These two circles and this common line uniquely determine a third circle, which is tangent to both circle and the common line. Let's say the third circle has radius R3. So what we need to do is find R3 in terms of R1 and R2. Is this problem difficult? No. we just repeatedly apply the lemma, and we have the results. Now, from circle of R1 and a circle of R3, from the lemma, we know the distance AC is equal to twice of the square root of the product of R1 and R3 is here. Now, if we consider circles of radius R2 and the circles of radius R3, the distance between C and B is the twice of the square root of the product of R2 and R3. And finally, circles of R1 and the circles of R2 are tangent to each other. Therefore, the distance between A and the B is equal to twice of the square root of the product of R1 and R2. However, we know AB, the distance between A and B, is the distance from A to C plus the distance from C to B. So we plug in the results we found. We have this one. Now divide both sides by 2 times the square root of the product of R1, R2, R3. This one becomes this one. Therefore, we have found R3 in terms of R1 and R2. If you are not comfortable with this formula and hope to find R3 explicitly, so we just add them together, and then we have this. Square it, we have R3 being this. So anyway, whether you like this one or this one doesn't matter, because we have represent R3 in terms of R1 and R2. So we solved problem 1 easily. Then let's move on to problem 2, which is an extension to problem 1. Now, given a circle, let's say OA with radius A, a second circle, OB, with radius B. And also, we have a common tangent line, so that OA is tangent to this common tangent line at A, and OB is tangent to this line at B. As we mentioned in problem 1, circles OA and OB uniquely determine a circle of radius R1. Now, if we use OA and R1, we are able to construct R2 with radius R2 and so on. This process can continue indefinitely. Somehow, we reached Rn, circle Rn of radius Rn. So what we need to know is, what is the radius of the nth circle in this sequence? In other words, from OA to OB, we have R1. From OA to R1, we have R2. From OA to R2, we have R3, and so on. Eventually, from OA to circle Rn minus 1, we have Rn. So our work is find the radius of circle Rn in terms of A and B. Is this difficult? Not at all. Many Japanese temple geometry has similar flavor. Given something, we are able to construct a sequence of similar figures. And then what is certain parameter in this sequence of figures? In the future, we will talk about more on this topic. So let's start our analysis. From OA to OB, we have R1. So the radius R1 is this. We found this in problem 1. Now from OA to R1, we could construct R2. So the radius of R2 is equal to this. That is, the radius of R2 is a function of A and the radius of R1. But we do know the radius of R1 is this. Now we see that we have two terms of 1 over square root of A. We just add them together. So the radius R2 has a relationship with A and B like this. Notice 2 here. This 2 agrees with the subscript of R2. This is not a coincidence. If you don't believe it, let's do one more. From OA and O2, we have O3 of radius R3. So the radius R3 satisfies this formula. This is the radius of OA, and this is the radius of R2. But previously we know R2 satisfies this. Keep this in mind, this 2 and the subscript of R2. Adding these two terms together, we have 3 over the square root of A. Isn't it interesting? This 3 agrees with the subscript of R3. So this is exactly what we want. So we make an assumption that for a circle Rn, its radius would satisfy this relation, n here and n here. How do we prove it? Of course, if you have a sequence like that, mathematical induction is the most natural way. So let's say in a mathematical induction, we have n equals 1, which is initial case. And then we assume the relation is true for n. From what we have learned, we prove that the similar relation also is true for n plus 1. So in this case, for n equals 1, that is the radius of R1. We know it is this and this. We have R1. So the base case is true. So let's assume that it's true for Rn. N here, N here. Is this relation also true for n plus 1? That's n plus 1 here and n plus 1 here. So let's say for circle Rn plus 1, its radius is 1 over square root of A plus 1 over the square root of the circle Rn. But because of this, 1 over square root of Rn is this. So we add these two terms together. We have this. Look at here. n plus 1, n plus 1. Therefore, our assumption holds for whatever the value of n is. Therefore, we established a very interesting relationship among OA, OB, common tangent line AB, and a sequence of circles that are going smaller and smaller indefinitely. This ends our section 1. If you are interested and would not hesitate to continue, please go with section 2 followed by section 3. And if you don't have time to continue, then just stop here. And later, come back for section 2. As we mentioned, section 3 is the most difficult and the longest section, in which you need to know something about parabolas, although we reviewed it a little bit. Okay, let's move on to section 2. Section 2 is a rather short section in which we will be talking about two similar problems, problem 3 and problem 4. Let's talk about problem 3. We have a big circle O with center O and radius R. And we have a chord. A circle O1 with center O1 and radius R1 is tangent to the big circle O at its north pole and the chord at the center point. And O2 is a third circle. This circle is tangent to O1 and the big circle O and the chord. And finally, we have circle O3 with center O3 and radius R3. O3 is tangent to O2, O, and the chord. So here we have 4 radii, R, R1, R2, and R3. Our question is, find R in terms of R1 and R3. Please notice that the radius R2 of circle O2 is not used. So circle O1 and this radius R1 are uniquely determined by the big circle O and the chord. Similarly, R2 is uniquely determined by O1, O, and the chord. By the same reason, circle O3 is uniquely determined by O2, O, and the chord. So, circle O2 is an intermediate circle whose purpose is to find circle R3. Therefore, circles O1, O2, O3 are closely related. And knowing O1 and O3, we should be able to find O2. Now, how do we find R in terms of R1 and R3? Look at here from the lemma. The distance between this tangent point U of O1 and V, the tangent point of O2 on the chord, the distance UV, or the length between U and V, is 2 times the square root of R1 times R2. By the same reason, the distance between V and W is 2 times the square root of the product of R2 and R3. So what we're going to do is find relations among R, R1, R2, and R3. Eventually, we eliminate R2 from this relation. As a result, we are able to find R. So the solution to this problem is divided into two parts. This is the part 1. We have a few lenses here. This is the radius. And the radius of O1 is R1. Therefore, the diameter of O1 is 2 R1. So suppose we drop a perpendicular from O2 to line O1, meeting the line at point A. So the distance from O to A would be the distance going from O to the midpoint of the core plus the distance here, which is this. And here we have R minus the diameter, that is 2R1. So the distance going from O to A would be R minus 2R1 plus the radius R2. Therefore, we have OA equals R minus 2R1 plus R2. AO2 is 2 times the square root of R1 times R2. And OO2 is the radius R minus the radius R2. Now, because this triangle is a right triangle, we have the square of OA plus the square of O2A is equal to the square of O2 is here. Plugging the value of O2, which is R minus R2. OA is R minus 2, R1 plus R2. And AO2 is this one, 2 times the square root of R1 times R2. So we have this relationship. This relation has R, R1, and R2 involved. So let's simplify this relation. Now we could expand this one. We see that R squared here and here are cancelled each other. R2 here and R2 here would also be cancelled. And when we expand this, we have 4 times R1, R2, which could be cancelled by this term. So after some simplification, we have this. Now, some other arrangement, this one becomes this one. Dividing both sides by 4, we have this, which means we have R times R2 being equal to R times R1 minus R1 squared. This one will be used in problem 4, the next problem. Now solving for R2, we have only one term R2 here. So R2 is represented by the use of R and R1. But this one does not involve R3. To find R3, we need to go to part 2. The idea is the same as part 1. Again, from the center of O3, we drop a perpendicular to the line O1, meeting it at B. So we have learned that this is R minus 2R1. Now, instead of previously R2 here, the distance going from O to B would be this distance plus this distance, which is R3. So here, OB is R minus 2R1 plus R3. Now, BO3 is the sum of this one from U to V and V to W. which is this one. Therefore, the sum of these two terms become 2 times the square root of R2 times the sum of the square root of R1 plus the square root of R3. So BO3 is this. And finally, OO3 is equal to the radius R minus the radius R3. So we have this. Because OBO3 is a right triangle, we have OO3 squared is equal to the square of OB plus the square of BO3. So plugging this value into this relationship, we have this. It looks complex, but indeed is not so. So let's copy the formula here. We try to find R2 in terms of R1, and R3. Find out, we have only one term, R2 here. So let's move this term to one side. So we have the square of this, which is 4R2 times the square of this, is equal to R minus R3 squared minus this term. Now we apply A squared minus B squared to yield A minus B times A plus B. So after simplifying it, we have this. Now let's take a look at this term. That is R2 times the square root of R1 plus the square root of R3 squared. So R square root of R1 plus square root of R3 could be part of this one, because R1 minus R3 can be considered as the square of the square root of R1 minus the square of the square root of R3, which yields square root of R1 minus the square root of R3 times the square root of R1 plus the square root of R3. So plug this part into here. Immediately we notice that we have this common factor. This one and this one. They cancel each other. As a result, the left-hand side becomes R2 times square root of R1 plus square root of R3. On the right-hand side, we have R minus R1 here and the remaining term here. Therefore, solving for R2, we have this. This is what we want in terms of finding R2 in terms of R, R1, and R3. So combine part 1, which is here, and part 2, which is here, together, because this one is equal to R2, which in turn is equal to this one. So the results here is equal to the results here, so R2 disappeared. And we also have a common factor, R minus R1. So eventually, after some simple simplification, we have R in terms of R1 and R3. This is our final answer. So this is the solution to problem 3. Representing the radius R in terms of the first circle and the third circle, using the second circle as an intermediate step. Then let's move on to problem 4, which is a variation of problem 3. As in the previous problem, we still have a big circle O of radius R and a core AB. O1 is the same, that is tangent to the north pole of O, and the midpoint C of the given chord. O2 is a circle tangent to O and the common chord and circle O1. But this time, we're not going to find the radius R. Instead, what we're going to do is find D, half of the length of the chord, in terms of R and R2. Here, R1 is not used. So basically, we have more term than needed, and one of which could be eliminated. So in problem 3, R2 was used as an intermediate step to find R. In this problem, R1 will be used as an intermediate step. In other words, we find a relation among R, R1, and R2, and D. Then we eliminate one of them, that is R1. Remember, we found this relation in part 1 of the previous problem. So that eliminated 50% of our work. Now look at this right triangle. D is half length of the chord AB. And here we still remember it's R minus the diameter of O1. So its length is R minus 2R1. So in this right triangle, we know R squared is equal to the square of this and the square of D. So D squared is R squared minus this square. Again, we apply A squared minus B squared being equal to A minus B times A plus B. So after some simplification, we have this, which is obtained previously. Now, we know that this term is equal to R, R2. So replacing this term by R, R2, we have D squared being equal to 4 times R, R2. Taking square root, of course, we will get D equals 2 times the square root of R times R2. So the chord length AB is twice of D, which is this. Notice here, this relation will be used again in problem 7, the last problem in this lecture. Finally, we reach section 3, in which 3 problems will be discussed. They are problems 5, 6, and 7. Section 3 is a bit long and a bit more challenging than the previous 2 sections. And also, section 3 requires some knowledge, the basic knowledge of a parabola. So if you do not recall what a parabola is and what are the basic facts about a parabola, please review your geometry book. Then, problem 5. This is probably the longest problem in this lecture, which is a bit more challenging than all previous problems. So, what problems 5 is? Given a line, fixed line, with 2 fixed points A and B. From any circle OA of radius A, we can always construct uniquely a circle OB of radius B, so that circle OA and OB are tangent to each other externally, and OA is tangent to the fixed line at A, OB is tangent to the line at B. So this is a configuration. We have OA, OB, they are tangent to each other externally. Both of them are tangent to the 2 fixed points A and B. respectively on a given line. So now let's consider several interesting scenarios. We have circle OA here, which is tangent to point A. And we are able to construct circle OB, which is tangent to the second fixed point B. And from OA and OB, we know we are able to uniquely construct a circle OR. Now, if OA gets larger to become this one, and definitely OB will become smaller, the constructed OR is smaller. If OA is even larger to become this one, OB shrinks further, and OR, which is tangent to OB and OA, becomes even smaller. If OA gets even larger, this one, this is OB, and this is OR. As you can see, the circles becomes smaller and smaller and smaller. And this is even larger OA, and even smaller OB, and this is OR. So as you can see, this circle becomes smaller and smaller and smaller. And yet, OA is tangent to the fixed line at fixed point A. OB is tangent to the fixed line at fixed point B. So this is very important observation regarding the fixed line and two fixed points, and the configuration OA, OB, and its derived circle OR. So we mentioned if OA goes larger, OB goes smaller. And if OA becomes extremely large, circle OB will become extremely small. In fact, when the radius OA is so large, the radius B of circle OB would become so small. When OA becomes so large, its radius A becomes nearly at infinity. Then the radius B of OB would approach to 0, which means when OA is so large, OB is just the point B, in which case circle OA becomes the fixed line OB, AB, and the circle OB is just a point B. So when does OR becomes the largest? When OA and OB are equal. That is when A and B are equal. Because if OA gets larger, OB becomes smaller, OR also becomes smaller. Because they're symmetric. When OB gets larger, OA gets smaller, its derived OR will become smaller. Therefore, OR reaches its maximum if and only if OA and OB would have equal radii. As a result, the radius of OR will satisfy this formula, which was discussed in problem 1. Therefore, 1 over the square root of R is equal to 1 over the square root of A plus 1 over the square root of B, because A and B are equal to for R to reach its maximum. Therefore, 1 over the square root of R is equal to 2 over the square root of A. Consequently, R is equal to a quarter of A or a quarter of B. So this value is the maximum radius for OR to have, in which case the radius of OA and OB are equal, and 4 times of OR. Now, because we know each pair of circle OA and OB uniquely determines an OR, there's an infinite number of circle pairs of OA and OB. Hence, there is an infinite number of circle OR. So, given a fixed line and two fixed points A and B, varying OA and hence OB, we have a whole lot of circle OR. So in this problem, we're going to find the relationship of these circles OR. Initially, it looks kind of vague, but indeed it's not. Now let's look at this configuration. We have equal radius OA and OB, and this is OR, the largest. So if A and B are equal, R is a quarter of A or B. So this configuration is symmetric about the midpoint of A and B. Actually, the whole configuration is symmetric with respect to the line perpendicular to AB and through the midpoint O of AB. So this is OA and this is OB. By symmetry, OA, we could use the same large size of OA for OB, and this is the OB corresponding to this one. So this one is constructed from the red OA and OB, and this one is constructed from the green OA and OB. So they are symmetric. So for convenience, let's say the length between A and B is 2D. Therefore, from the midpoint O to either A or B is D. We will be using D exclusively in subsequent discussions. Now, because of symmetry, we have this 4, D over 4, that is the largest OR here. We use O D over 4 to represent the largest one. And this OR with radius R equals to R of X. What does this X mean? X is the distance from the midpoint O to a tangent point. And the distance here is X. So if a configuration of OA and OB exists, there will be a circle OR. So given this distance X, what is the radius of this OR? This is what we are going to figure out. If we could figure out the radius of this OR, we are able to figure out the locus of its center. So we will prove the following. The locus of the center of all circles OR is a parabola, and all of these OR circles are tangent to a common circle. Let's go for the first one. We have an OA, OB here. This pair of OA, OB derives a circle OR. So given X, how could we determine the radius of this R? In other words, given a distance X from the midpoint, find the R so that circle OA and OB and OR can be constructed. They all are tangent to the given line, so that OA is tangent to the line at A, OB is tangent to the line at B, and OR is tangent to the point with a distance X to O. And of course, OA, OB, and OR are tangent to each other. So, from OA and OR, we use the lemma again. OA here, OR here. The distance is D plus X. This distance D plus X is equal to twice of the square root of the product of radius A and the radius R. Solving for A, we have this. So the square root of A is equal to D plus X over 2 times the square root of r, where r is to be found. Now, look at OB and OR. The distance between the tangent point is d minus x. This distance is equal to 2 times the square root of the product of b and r, which is here. Solving for b, we have this. And for the third case, we look at circle OA and OB. The distance between the two tangent points A and B, which is 2D, is equal to 2 times the square root of the product of the radius of A, the radius of circle B. So we have this. Now, D is equal to the square root of A times B, which is also equal to the square root of A multiplied by the square root of B. We have learned the square root of A here and the square root of B here on previous slide. So how about we plug A, square root of A here, square root of B here. Then we have this. This was found to be the square root of A. This was found to be the square root of B. So multiply them together, we have D equals 1 over 4r times d squared minus x squared. Because what we want to find is r, so we move r to the left-hand side, d to the right-hand side, we have this. In other words, what we have found is very important. Given a distance x from the midpoint O, a circle with radius r, which is equal to this, can be constructed. If this circle is considered to be OR, then a circle OA tangent to OR and at A, and a circle OB that is tangent to the line at B and also tangent to the circle OR can be found. So we know the value of R is determined by the half length of AB and the position of the tangent point. This is a second degree equation. The normal form or standard form of a parabola in Cartesian coordinates is y equals 1 over 4 times f times x squared. This is a parabola. And this is the x coordinates, and this is the y coordinates. From this equation, we know the origin is on this parabola. And given this formula, we know the focus of this parabola is at 0, f. The directrix is the line y equals negative f. If the value of f is positive, the opening of this parabola is up. On the other hand, if f is negative, the parabola is down. So for any point P on the parabola, the distance to the focus and the distance from P to the directrix are equal. These are the basic facts of a parabola. Now, this equation is a parabola. So let x-axis be this one, be the x in the equation. And the y-axis is for r. From this equation, we know this parabola intersects the x-axis at d, 0 and negative d, 0. And because it's negative, so the opening of this parabola is downward. This parabola also intersects the r-axis at 0, d divided by 4, which is simple to know. Set x to 0, you get r. And if we translate the parabola downward, so that V would be at the origin. So we found the focus point is negative 3/4D. So the focal length distance between the focus and the directrix is D. Now, we discuss the parabola based on analytic geometry. Can we do it without coordinates? Of course we can. So we know the parabola of the center of the circle OR passes through B when the radius of B is 0. And also passes through the vertex of the parabola V when OR has its maximum radius, which is D/4. So let the focus be F somewhere here. We don't know how large it is. The distance from the vertex V to F is also equal to this value. So we want to find out what this value is, what this value is, and what value is from the focus F to B. So for convenience, because these two distances are equal. Why? This is because from the vertex to the focus is equal to the distance from the vertex to the directrix. And we have already know that this is the center of the largest circle OR. So this segment is D/4. This segment is also D/4. Let's say the unknown distance from this point to the directrix and the distance from O to the focus be T, which is unknown. And the distance from the focus to B, let's say is K, which is also unknown. In this way, the distance from the vertex V to the directrix would be T plus D/4. The distance from OB to the directrix is T plus 2 times D/4. So it is T plus D/2. The distance K from focus F to B is equal to the distance from B to the directrix, which is of course T plus D/2. So the two unknowns are T and K. Now, because triangle FOB is a right triangle with a 90-degree right angle here, therefore K squared is equal to T squared plus D squared. Remember, D is the distance from the midpoint of the given segment AB to B. And we also know K is equal to T plus D/2. T plus 2 times D/4. So plug K into this one, we have this. And this T squared here and here are cancelled out. We have a D squared here, a D squared here. Eventually, we found out T is 3/4 of D. And the value of K would be T plus D/2, which is 5/4 times D. Therefore, the value here is 5/4 times D. And the distance here is 3/4 of D. So this is what we know so far. The locus of the center of the circle OR is a parabola with the following properties. The vertex is V. The center of the largest circle OR. The focus is F, which is 5/4 times D from the vertex. The directrix is the line perpendicular to VF. at the distance of 5/4 times d from the vertex F. Now, let's consider a circle that is tangent to OB, whose center is on the parabola. Remember, the center P of this OR would have equal distance to the focus and to the directrix. Therefore, the distance from FQ is equal to FP plus FQ. But of course, FQ is the radius, because this line going through the center to a point. So this is a radius R, this is radius R. Therefore, the distance going from F to Q is equal to the distance of FP plus R. But because P is on a parabola, so FP is equal to PS. Therefore, the distance going from F to Q is equal to the distance from the line OB to the directrix, which is a constant for a parabola. So this distance is 5/4 times d, which is a constant. So what does that mean by FQ being a constant? Now, if any circle OR with center on the parabola P, so the line leading from F to the center to the other end of the circle is always a constant, which means the circle is tangent to the circle here, because the distance is always the same, the radius of a circle. And this distance is exactly the distance going from F to B. So this proves that not only the center of circle OR lies on a parabola, or circle constructed in such a way are tangent to a common circle with center at F and the radius 5/4 times d. This is the end of problem 5. Now, we move on to problem 6, which is a variation of problem 3. We use some idea from problem 5, and then problem 5, problem 6 together would yield a sort of converse of problem 5. In problem 3, we are given a circle O with radius R, and a circle O1 tangent to the north pole of O and the midpoint of the given core, and a circle O2 that is tangent to O, the common core, the core, and O1. And then we construct a third circle O3 tangent to O, the core, and O2. Then the radius R of O can be computed by only using the radius R1 and the radius R3 without R2. This is what we did for problem 3. In other words, radius R is a function of R1 and R3 only, with an intermediate step of circle O2. So our question is, what if O3 is an arbitrary circle tangent to the core and circle O? We don't have circle O2 in this figure. So the question is, given a circle O and a core, and the circle O1 tangent to the north pole of O and midpoint of the core, and the arbitrary circle O3 tangent to O and core, is it possible we represent R by only using R1 in R3? The answer is yes. If we could find R, we are able to find the location of O. Because we have 2R1 here, and the distance from the midpoint to the center is R minus 2R1. And also, the center of O3 lies on a parabola. So its vertex, the focus of this parabola is O1, the vertex, and the focus O. So we still need some notifications. Let the center and the radius of O be O and R. Let the circle tangent to O and the core at the midpoint be O1, with center O1 and the radius R1. And an arbitrary circle O3 that is tangent to O and the core. And this circle has center O3 and R3. From O3, let's construct a perpendicular to the line of O1, meeting the line at C. So we know this distance here is R minus 2R1. So the distance going from O to C is R minus 2R1 plus R3. Let the distance from the midpoint of the core to the tangent point of R3 on the core be X. And of course, because this circle is tangent to O, so connecting the line going from O to O3 and extend to the tangent point, these 3 points are collinear. And this distance is, of course, R minus R3. So because triangle OCO3 is a right triangle, we have O3 squared is equal to OC squared plus CO3 squared. Therefore, we have R minus R3 is the length of O3, and this is the distance of OC, and X squared is here. So, expanding this formula, we again use A squared minus B squared, which is equal to A minus B times A plus B. Simplifying, we have this. We will be using this in problem 7, the next problem. So R is unknown. Solving for R, we have this. Here we still have R1, R3, but we have an X. X is the distance from X is the distance between the two tangent points. Now, center O is located R minus 2 R1 from the tangent point on the core. So this distance is calculated as R minus 2 R1. So we have this. So the location of O is fully determined. We learned in problem 5 that the locus of the circles that are tangent to O and the core is a parabola. That is, O3 lies on a parabola. Of course, in this case, R3 must be less than or equal to R1. It must be non-negative. So L is the line parallel to the core at the distance of R from the core. Therefore, the distance from the North Pole to L is R minus 2R1. Now we have that the distance from O3 to O and the distance from O3 to L are equal. Both are equal to R minus R3. Because O3 is an arbitrary circle tangent to circle A and the core. And because the distance of O3 to L and the distance from O3 to O are equal, O3 lies on a parabola. The vertex is here, and the focus here, and the directrix is here. So, from an arbitrary circle that is tangent to O and a core. We know that its center lies on a parabola with focus, vertex, and directrix. Now, then we're going to build a converse of problem 5 from problem 5 and problem 6. Again, given a circle O and a core AB of length 2D. So our question would be, what is the condition for a successful construction of OA, OB, and OR triplet? Recall that in problem 5, we have a core to fixed point. OA is a circle tangent to the core at A. OB is a circle tangent to the core at B. And OA, OB are tangent to each other. So this OA, OB, and the core uniquely determines AO3 or OR. So the converse is because all of these ORs would be tangent to a common circle and their centers lies on a parabola. So the question is, now we know we have this common tangent circle and the locus on a parabola. So given a arbitrary circle, O3, consider it as OR. What is the condition for us to construct an OA and OB and this O3 to be used as OR? So let's use the diagram of problem 6. And we use the same notation. So O3 is the circle OR in problem 5. So restate our question as follows. Given O3, can we find OA and OB such that OA, OB are tangent to AB at A and B respectively, and they are tangent to each other, and also O3 is tangent to OA and OB. Definitely, it's not always the case. Given in a circle, arbitrary circle, O, and a circle tangent to O and a common core, it may not be able for us to construct OA and OB so that OA, OB are tangent to A and B, and they tangent to each other. And also OA, OB, O3 are tangent to each other. So if that's the case, what is the condition for us to make such a case? This is what we are going to do. So we learn from problem 4, D squared is equal to this. D is the half length of AB. Therefore, solving for R, we have this. From the previous problem, given x, which is the distance from between the two tangent points, so x squared is equal to this. That's what we obtained from problem 6. Now, problem 6 has R3 involved. Let's solve R3. We have this. In problem 5, we show that at this distance x, if OA and OB can be found to tangent to AB at A and B, and also tangent to OR, that is currently the circle O3, then the radius R, and in our case R is R3, must satisfy this condition. In other words, if the radius R3 satisfies this condition, then OA and OB can be constructed. So the R3 we found here and the R3 we obtained on the last slide must be equal to get OA, OB to satisfy our condition. So This is what we found here, and this is what we found on the last slide. Solving for R1, we get this. In other words, this circle and this chord cannot be arbitrary. R, in order to find OA and OB to satisfy our condition, R1 has to be a quarter of the half length of AB. This is the condition for us to find the converse of problem 5. So our conclusion is, if R1, the radius of O1 is a quarter of half length, that is R1 equals D over 4, then any circle O3, there exist circles OA and OB, which are tangent to A and B respectively, and OA, OB are tangent to each other, and O3 is tangent to OA and OB. So this is the condition we want to find. Therefore, this is at least sort of a converse of problem 5. So, in summary, what we have done so far is the following. Given a line, fixed line, and two fixed points A and B, circles OA and OB that are tangent to each other and also tangent to the line at A and B respectively, they induce a sequence of circles that are tangent to OA and OB and the common chord. The consequence is the largest of such circle would have a radius D over 4, where D is the half distance of segment AB. And these circles would have their centers on a parabola. And also, they are tangent to a common circle. The parabola has a directrix and a focus. The focus is exactly the center of this common circle. So, the vertex of this parabola is the center of the largest OR. And the distance going from V to O is equal to the distance from V to the directrix. Therefore, from a sequence OA and OB, a sequence OR is determined. And this sequence of OR gives us the largest radius must be D over 4. The center lies on a parabola. All of these small circles are tangent to a common circle. On the other hand, given a circle and the common chord A and B, if the half length here is equal to D over 4, here D is the half length of AB, then every circle tangent to the chord and the given circle would have their center lies on a parabola. And each of such circle uniquely determines a pair of circle OA and OB. This OA and OB are tangent to each other and tangent to line AB at A and B respectively. To get this condition satisfied, the largest circle must have its radius D over 4, where D is the half length of the chord length AB. So this is the converse of problem 5. Let's divide everything into steps. We introduce a simple. Given 2 points A and B, which connects to have a fixed line. C of CA, OA, OB, OR, given AB, is the set of circles that contains all triplets of circles OA, OB, and OR, such that AB are tangent to each other, and OA is tangent to the line at A, OB is tangent to the line at B, and OR is tangent to OA and OB and the line AB. This is a set of triplets OA, OB, OC. So what we have done so far is given two fixed points A and B, and the half length of segment AB is AB divided by 2. Then these pair of circles OA, OB would induce a third one, OR. Therefore, for every A and B as a pair of fixed points, these triplets sets do exist. From here, we know the largest circle OR has radius d over 2. From here, we also obtained that OR are tangent to a common circle and their centers lie on a parabola. This is problem 5. On the other hand, given two fixed points AB and D is equal to half of the chord length, if the largest circle OR has radius d over 4, then we are able, from each of these circles, we are able to construct a triplet. So going from here, we have a set of triplets. This triplet implies the radius and the existence of a common tangent circle and a parabola. On the other hand, if the largest circle OR has a radius d over 4, then these triplets exist. If the largest circle OR does not have radius d over 4, then, no such triplets exist. So that finishes our discussion of all 7 problems. So what we have learned, we discussed 6 related problems, all of which are part of the Japanese tempo geometry problem. The 7th is the converse of the 5th, which is not discussed in the set of Japanese tempo geometry problems. All problems are similar. It has a common flavor. Find the radius of circle that is tangent to some circles that are tangent to each other, satisfying certain conditions. In some cases, the locus of the center of these circles is a parabola. We'll review the basic facts of parabola. We will encounter similar but more challenging problems in the future. So, these problems are taken from these 4 references. This one is the first one, Fukagawa's book. And then a more comprehensive talking about history and so on book was published in 2008. And reference 3 and 4 can be found on this Japanese side, but it has English side as well. So the link here is for the English side. There is a book translated from Japanese. It's called Japanese Tempo Mathematical Problems in Nagano Prefecture, Japan, published in 1999. And there is another very interesting one, Formulas in Traditional Geometry, published in 1841, more than 100 years ago. The correspondence between these book problems and the problems discussed here are as follows. The lemma is taken from 1989 Fukagawa's book. Problem 1, problem 2 are also from Fukagawa's book. And problem 3 is taken from the Nagano Prefecture problems. Number 4 is Formula 29, and problem 5 is from Fukagawa's book. Problem 6 is a variation of 3, Problem 7 is a converse of problem 5. You may find these problems from the above mentioned references. And the book or the ebook or the PDF version of this book and this books are free from the Japanese Wasan website. This is the end of episode 3 of the elementary geometry lectures. Hope you like it. See you in our next episode. Goodbye and good luck.